And today I'll be talking about sizing photovoltaic systems in SAM. The webinar will be about 40 minutes long, with 20 minutes or so for questions and answers at the end. And the webinar will also be recorded. The recording, as well as a copy of the slides, will be available on the SAM Learning page. Before getting into the webinar, I want to remind you that this webinar is part of the 2015 SAM webinar series, which you can see listed here. This schedule can also be found on the SAM Learning page. And from there, you can register for any of these free one-hour webinars. If you can't make a webinar that you're interested in, don't worry. We also plan to record and post all of these webinars after they're given so that you can listen at your convenience. But we encourage attending them if you're able to so that you can ask any questions you might have in person. So today I'll be covering a couple different topics for PV sizing. I'll go ahead and do a bit of a demo in SAM itself of what the workflow looks like for sizing PV systems. Then I'll go into a little bit of the issues around sizing your system from a DC or direct current side to the AC or alternating current side. I'll talk about sizing distributed systems for an electric load and some of the limitations of the SAM software when it comes to system sizing. And as I mentioned, we'll have some time at the end for a Q&A session. So like I said, I think the most useful way to get started with this webinar is actually to take you through the user interface in the latest version of SAM and show you where all of the relevant pieces are when you're sizing a system. But before I do that, I'll quickly hit on a few of the basic definitions for some of the sizing terms. But I promise that it's only 2 slides if this is too basic for some of you. There are several different ways to define the size of a PV system. PV modules, as you probably know, typically produce DC power. Therefore, the total DC capacity of the modules in a PV system can be one way to define the size of a system. This is how nameplate capacity is defined in SAM. The DC power from the modules are then typically fed into an inverter to transform the power from DC to AC before it is fed into the grid, substation, whatever. The total rated AC output of the inverters is then another way to define the size of the system. And it's important to note that some people will define nameplate capacity as the AC capacity of a system. Sometimes the AC and DC capacity of a PV system may be the same, but not always. So the ratio between the DC and AC capacity is called the DC-AC ratio. So now I'm going to switch on over to SAM itself to do a little bit of a demo for what you actually go through when sizing a system in SAM. I'll go ahead and start a new PV residential project, just as an illustrative case. And I'll skip right to the system design page because this is where most of the sizing happens. I'm going to ignore the subarray options for now and deal only with sizing the system as a whole, which are all of the relevant inputs are contained in these top 2 boxes. There are 2 options for sizing systems in SAM. You can specify your exact size layout with this option on the right here. So the number of modules per string, the number of strings in parallel, and the number of inverters that you have. Or you can choose to specify the desired array size. And I'll point out that the information about your current system size is contained in these blue boxes here. So this will tell you the total number of modules currently in your system and how they're laid out, a little bit about their area, and then some about the inverters. Now when you select the Specify Desired Array Size option in SAM, it is calculated automatically by SAM adhering to a few rules. First, Sam determines the number of modules in a string by aiming for the middle of this maximum power point range shown here in the inverter characteristics. And it uses the maximum power of the module to figure out what the voltage will be for the string. Once the number of modules in a string is determined, Sam will then calculate how many strings there should be in parallel to get you to this, approximately to this desired array size. And then finally, the total number of inverters is calculated based on this DC to AC ratio, which I defined in the slides. I want to note that all of these calculations are based on the maximum rated power point values of the modules and the inverters, and that Sorry, we seem to be having a little bit of technical difficulty, so I'm going to just repeat my last sentence in case it didn't go through. I'll note that all of these calculations I just mentioned are based on the values of the modules and inverters, and that these values are calculated at module reference temperature and irradiance conditions that may not be representative of what your system will actually experience in the location that you've selected. However, SAM doesn't have any better information about those conditions without running a simulation. So this serves as a good starting point of how you might want to size your system. One thing to notice when you're specifying a desired array size and DC to AC ratio is that SAM usually cannot size a system to the exact DC to AC ratio that you specify, especially for smaller systems. This is because you have to use a whole number of PV modules and inverters. And because of that, the possible DC sizes of your systems are discrete numbers. And likewise, the possible AC size of your system are also discrete numbers. So it may not be possible to get the desired DC to AC ratio exactly without going to huge numbers of modules and inverters. And by that time, especially for small systems, you're nowhere near the desired array size. And even apart from that limitation, no algorithm is ever perfect, including this sizing algorithm. So it's a good idea to keep an eye on the configuration at reference conditions down here, and also this sizing messages box, to see what the actual DC to AC ratio and DC nameplate capacity are for the system configuration that SAM has calculated. So if you've started out with this specified desired array size, you may then want to tweak the design a little bit based on what SAM has automatically calculated, like I said, using this as a starting point, to optimize the design closer to your specific requirements.
So we're noticing on the chat window that some people aren't seeing the full side of the screen, and so I don't know, that might work better.
All right, let me resize here.
Are you on the webinar? Yeah. So I think that.
Okay.
You got a little more room.
Screen a little bit. Hopefully that fixes it.
Yeah. Just the left few.
The left few inches.
Okay. Yeah. Now you're.
Let me just put it
there
in the middle. Right, okay. Well, I'll just keep it in the middle then. And hopefully that'll, yeah, that is sort of weird. Okay. Excellent.
If viewers notice additional issues, please feel free to note those in the chat, of course.
Okay. So getting back to our system sizing. Like I said, if you want to use the automatically sized system as a starting point, then you can note the number of modules per string, strings in parallel, and inverters, and go ahead and add those in over under the specify modules and inverters side. So we had 8 modules per string, 5 strings in parallel, and 2 inverters. So with this configuration that Sam calculated automatically, you'll notice that the DC to AC ratio is pretty close to the 1.1 that was originally specified, but that the nameplate capacity is only 8.6 kilowatts DC, when the one specified originally was 10 kilowatts DC. So let's say that you actually need your system to be a little bit closer to 10 kilowatts DC. So we'll go ahead and see what happens if we bump up the number of modules per string. So you can see now that the system capacity is much closer to 10 kilowatts. But the DC-AC ratio, which was pretty close to 1.1 before, is now 1.2. So this is the point for me as a designer to make a decision of which I care more about, the desired array size or the DC to AC ratio. Another thing I'll show just for demonstration purposes is what would happen if you accidentally specified something like 20 modules per string. You'll note that the sizing messages window gives new information that the inverter voltage was exceeded and that you should consider using fewer modules per string. These warnings may help provide the boundaries of what system configurations are most reasonable in your design. Now, although most of the system sizing happens on the design page, these are not the only factors that impact system sizing. All of these parameters are highly dependent on the exact module and inverter model that you select. So I'll go ahead and go back to this specify desired array size option, and then I'll go change my module and inverter. So let's pick one. We're currently at one with a maximum power of 215 watts. Let's switch over to one that has a maximum power of 200 watts. And for our inverter, let's pick one that's fairly close. Instead of a 4 kilowatt inverter, we'll go with a 3.5 kilowatt inverter. And then we'll go back to the system design page. So you'll notice here that with the same desired array size and DC to AC ratio, this time Sam calculates an array that's much closer to 10 kilowatts, but a DC-AC ratio that's much further away from the specified 1.1. This is due to the new sizes of your components and their rated voltages. So it's always important to keep in mind, if you're changing components in the process of designing a system, to always come back to the sizing page and recheck that the sizing ratios are consistent with your project requirements. So now that we've gone through the workflow of sizing a PV system in SAM, I want to talk a little bit more about the DC-AC ratio that I was mentioning. This is an example to illustrate some of the limitations of the DC to AC ratio that I was mentioning earlier, about how you're working with discrete sizes or discrete numbers of PV modules and inverters that are specified sizes. So for instance, in this example, with a desired system size of 100 kilowatts and a desired DC to AC ratio of 1, you basically have two options. Your number of modules, which is 58, gets you pretty close to that 100 kilowatts DC, but the number of inverters is problematic. If you have 3 inverters, your DC to AC ratio is 0.92. But if you go back down to 2 to try and bump up your DC to AC ratio, the actual ratio you get is 1.39. So again, this is a decision point where you have to decide which configuration is going to be better for your purposes, or if you need to change something like the number of modules or the module or inverter model. So at first you might assume that the target DC to AC ratio should always be 1. However, there are a variety of scenarios in which the ideal DC to AC ratio might not actually be 1. One thing to consider is the price difference in different inverter sizes. For example, say you have a 475 kilowatt DC system. There may be a 475 kilowatts AC inverter out there, but maybe the 500 kilowatt AC inverter is actually cheaper because it's a more common size. So you choose to buy that inverter for your system instead. This would change your DC to AC ratio to be a little bit less than 1 for cost reasons. Another thing to consider is inverter efficiency. Because inverters cannot convert DC power to AC power with 100% efficiency, a higher DC capacity is needed in order to reach the inverter nameplate capacity at reference conditions. If your inverters are 100 kilowatts AC and your system is 100 kilowatts DC, you will likely never actually produce 100 kilowatts AC power, even though that's the nominal rating of your inverter. This is where the DC power rating of the inverter is helpful, which is shown on the inverter page in SAM, shown here. The inverter DC power rating will tell you what your DC system must be rated in order to produce the AC rated power at reference conditions. Another scenario where the right DC to AC ratio for your system might not be 1 is if you're expecting significant PV module degradation. As an example of this, say you have a 10 megawatts DC system, but you're expecting your PV modules to degrade 10% in the first year. Perhaps you only install 9 megawatts AC of inverters, because after the first year you don't think your system will produce more than 9 megawatts. And the price difference is such that it's worth the lost power in the first year not to have to pay for additional inverters. So you may specify a DC to AC ratio higher than 1 so that by the end of your system lifetime, your inverter isn't incredibly oversized for your system. A third scenario that could affect your selected DC to AC ratio involves a little bit more financial analysis. Modules only produce their rated power at their rated temperature and irradiance conditions, and it may be that your project location doesn't experience those conditions frequently. In that case, your modules will be producing less than their rated power, which can be handled by a smaller inverter. During the few hours where your system does experience rated conditions and the modules produce full rated power, this smaller inverter will clip the power that is produced, meaning that some of the DC power produced by the modules is lost and not converted to AC power by the inverter. This SAM time series plot shows an example of that. The blue line is the DC power produced by the modules, and the orange line is the AC power produced by the inverter. You'll notice that the orange line tracks the shape of the blue line fairly closely, although slightly lower in magnitude due to the inverter efficiency that I mentioned earlier. At noon on the second day, however, the orange line flattens out as the blue line reaches its peak. This is when the modules are producing more DC power than the inverter can convert, and the inverter flattens out at its maximum AC power. The red line at the bottom shows the power that is lost due to this clipping. You can see that it's a fairly small amount. The question then becomes, is the total revenue lost due to inverter clipping more or less than the cost of buying a bigger inverter or more inverters? You can do this type of analysis for the first year in SAM by comparing simulations with different sizes and costs of inverters. Unfortunately, SAM cannot currently perform this analysis for the lifetime of the system, and I'll get into that a little bit more later. A final thing to consider when selecting your DC to AC ratio is how it affects the voltages that your system will experience. System performance is greatly reduced if the inverter is not operating within its maximum power point tracking range, which is a range of voltages that the inverter can take to stick on the MPPT algorithm. Another consideration is that if your DC system voltage exceeds the maximum inverter rated voltage, your inverter could be damaged, or you could void the warranty on your inverter so that if something does happen to it later, you can no longer get a warranty fix for it. The DC voltage experienced by an inverter is impacted most directly by the number of modules per string, but it can also be affected by the selected DC to AC ratio, especially if SAM is set to the mode where it automatically sizes the system. So everything that I just talked about may seem like a lot of information to keep track of, but to help you do that, we've added an inverter sizing information macro to the PV model in SAM. If you set up your case as you want it, then go to the Macros button under the Simulate button, you'll see a list of macros, one of which is called Inverter Sizing Information. Running this macro will run a simulation of the system that you have set up in the case in SAM and produce an HTML window like the one shown here with a bunch of information about inverter sizing. Some table cells are also automatically highlighted, like you can see here with the orange and red cells, when they are above certain threshold values in order to help draw your attention to results that you may want to investigate further or that may cause you to consider changing your design. And finally, as with all macros in SAM, if you are a scripter, you can edit the macro to add or remove information from this HTML window, change the threshold values that cause things to highlight, etc., to fit your individual or company requirements. So at this point, I'd like to change gears a little bit and talk about another aspect of PV system sizing in SAM, specifically for distributed systems. This will focus less on the DC versus AC and string configuration aspects of sizing a system, and focus more on the big picture question of how large should my system be. I also want to clarify at this point that our discussion will be focused exclusively on distributed grid-tied PV systems, as SAM does not currently have the capability to model off-grid or battery storage systems. For distributed systems, the primary goal is to offset some or all of your building's energy usage. Therefore, in the SAM residential and commercial financial configurations, you can specify an electric load that the PV system you're designing will help offset. In these cases, the ideal PV system size depends on a few factors. On the one hand, the end goal is frequently to offset 100% of the building's electric load. However, on the competing side, there are space and budget constraints, and there may also be requirements imposed by the local utility that owns the grid to which the system will be tied. The ideal PV system size will generally offset as much of a building's electric load as possible within the given space, budget, and any applicable utility constraints. So what I'd like to do next is to go back to SAM and quickly go through the options for inputting these considerations into SAM. So here I will go back to my PV residential case, which I hope is still viewable on the screen. Looks like it is. And I'll go down to this electric load page here. So there are a few different ways to tell SAM what electric load your system is going to be offsetting. They're all located on this same electric load page, although there is a macro that has to do with one, which I'll demonstrate in a minute. The first option is to input an hourly time series load. I'm sorry, it can be hourly or it can also be sub-hourly when you hit this Edit Data button. And you can copy and paste or import and export your values. Another way to get this hourly load profile, if that information is a little bit too granular for what you have access to, is to go into the macros section that I talked about earlier and pick this Download Electric Load macro. This macro will download an hourly load file from the NREL OpenEI residential and commercial building load databases. And it will apply it to the hourly electric load input page. So this can be a pretty nice option. In the residential system, there are 3 types of buildings available: base, high, and low, referring to their energy usage. So the base is the base energy usage, high means higher than base energy usage, and low is lower than base. An important thing that I will note here is that base is actually based on a residential building built in 2010. So this only actually represents a small portion of the population. If your house was built previously to 2010, this might not be an accurate electric load for your type of building. So it may be more accurate, depending on the age of your home or building, to base your hourly load on the high option. I'll go ahead and hit run macro just to demonstrate what happens. And it will go ahead and download the OpenEI hourly data and apply it to the electric load input page, and then give you this nice message box to tell you that it was a success. So I'll go ahead and hit OK and go back to this electric load page and take a look at the data that it has supplied. So there it is. Now, because these are data sets that are more average or representative of various residential building types and not necessarily your home, it can also be incredibly helpful to scale these hourly values to monthly utility bill data. This is an option that we had in previous versions of SAM, and we do plan to add it back into this version of SAM for our next release. In the meantime, we also have written a script that will scale the hourly values to monthly values that I believe is available on the help page at the moment until our next version comes out that includes the monthly scaling in this input page. The other option for inputting load data that I want to show is only available for the residential model, but it is this calculate load data page. And this building energy load profile estimator takes a variety of inputs about your building, including a couple of building characteristics, what type of electric appliances you have, and how you have the temperature settings set in your home. And then it also takes the monthly load data, say from a utility bill, for your home. And it uses all of these to create an hourly profile that it then scales to match the monthly data that you have input. And I'll point out that on both of these load options, there is a View Load Data button. And if you go ahead and hit that, it will bring up the SAM data viewer showing your hourly load profile. And you can zoom in on sections and take a look at what it looks like so that you get a little bit of a preview of what the load is that you've input before you actually run a simulation. So now that I've gone through the input options for the electric load, I'll go ahead and go back to my slideshow here. Another important aspect for sizing your PV system for your electric load is your electric utility rate. This will determine how much you would otherwise be paying for the electric load that you just specified, helping you to figure out the cost savings that you'll be getting from your PV system. There are a variety of rate structures that this input page can handle, some more complex than others, and it does make the page look a little bit complicated as a result. However, there is one simple method that I'll point out, and that's located in this top box here. The OpenEI Utility Rate Database linkage from SAM, where you click on this Search for Rates button, and it will allow you to search for and download the rate structure from your specific utility provider. And then it will automatically apply that rate structure to these inputs in SAM. So that can be one of the easier ways to fill in the inputs in an appropriate way for your residential building. So I also mentioned that budget constraints have a good deal to do with sizing a PV system. The best way to tackle the budget constraints is probably fairly obviously by putting them in the system costs page. Multiple different categories and ways to input system costs are located on this page. So you can input them as fixed costs, costs per watt, costs per module area, and then there are some costs that are implemented as a percentage, such as contingency and sales tax, etc. If you input most of your costs as per watt costs or percentage costs, you can allow the cost of your system to change as you change the system size to see what will best fit your needs. I also mentioned that space constraints are sometimes a factor in sizing your PV system. So I'll point out that SAM provides a little bit of information about this as well on the system design page. It will give you the total module area, which is based on the dimensions of the module that you have picked. And it also calculates a total land area based on the ground coverage ratio of the system that you specify. SAM only uses the total land area in calculations if you specify a dollars per acre cost on the system costs page that I just showed. But it does calculate the land area, which can be a little bit of a useful metric for you to take a look at if space is one of the constraining factors for your system. So now that you've input all of these various considerations and you've run a simulation, what results do you actually care about? On this screen, I show the metrics table on the right-hand side, as well as one of the graphs that is automatically created by SAM when you run a residential PV simulation. The metrics table provides a few quick numbers that may help you determine whether you've sized your system as you want it or not, including the net savings that you'll get with your system, what your payback period will be, and the initial cost of your system. The graph compares on a monthly basis the energy that you're producing with your system to the electric load that you have input and the credit you'll be getting from your utility. In our last SAM webinar, the Introduction to New SAM, I went through the many ways in which you can view and compare results. So I'll refer you to that webinar if you're interested in learning more ways to look at the results of your simulation. A recording of that webinar is available online, accessible from the SAM Learning page. But in the meantime, the main results page can give you a few quick metrics to look at to get an idea of whether this is the system that you are hoping it is or not. What I really want to point out next, though, is that after you've looked at the results of your simulation, what if it's not quite what you were looking for? How can you optimize your system size for the results that you're looking for? One of the things provided in SAM that can help you do that is this parametric analysis option, which is located under the Simulate button in the bottom left-hand corner of the SAM window. By varying your desired array size as an input and looking at your metrics of interest as outputs, which might include the initial cost, year one savings on your electric bill, or others, you can start to hone in on the system size that is best for your particular situation. Details of how to run a parametric simulation are again in the previous webinar, which you can access from the learning page of the SAM website. The last thing I want to touch on are some of the limitations of the SAM software when it does come to system sizing considerations. While SAM does a great many things, there are some considerations that the software currently cannot account for. And I want to make sure to mention those here for you to keep in mind as you run your SAM simulations. So there's a bit of a list here. I'll go through each one briefly. First thing I should point out is that SAM is not a full electrical model of your system. So there are some sizing limitations inherent in that fact. It also does not show frequency effects being not a full electrical model. And it does not properly model inverter operation if the string voltage is outside of the MPPT range of your inverter. A few other considerations are that SAM assumes that the grid can handle any level of power that the distributed system has created, which may not always be accurate depending on the utility. SAM also does not calculate wiring losses due to system size. They are input as a percentage loss currently, which may or may not be accurate depending on the size of your system. As I mentioned previously, SAM cannot currently model standalone systems. The systems that you model must be grid-tied. And the final consideration is that SAM does not model lifetime power production. SAM models first-year power production, and then on an hourly basis. And then degradation is applied to each year in the out year to each hourly total. This is not necessarily an accurate representation of real life, where degradation applies on the DC side of the system, and so that might change the clipping behavior of your inverter in the out years. But this is not a capability that SAM currently has, so that is also listed as a limitation. So with that, I've finished up just a couple minutes shy of that 40 minutes I was aiming for. I'd like to thank everyone for your attention and open it up for Q&A at this time.
Great, thanks, Janine. This is Paul Gilman. If you have a question, if you could type it in the chat window, and then we'll unmute your line if you have a follow-up question, that'd be great. You could also raise your hand if you want to use the little hand-raising icon in the list of participants. I don't want to unmute all the lines, or we'll get a lot of noise, and it'll be hard to hear. So here I see a question. I'll unmute you. You got it, man. Okay. Go ahead, Ihor.
Hello. Yeah. Can you hear me?
Yes. Go ahead.
Awesome. I asked one question in chat, and I want just to expand on that. My question is about maximum power of inverter and nominal power of inverter. I'm not sure if there's the correct representation in the CEC database. It's just like some of the model of the inverters, they, for instance, like if you pick like regular standard SMA 500, so like it's known that nominal AC rating of that particular model is 500. But then, like if you go into the details of that model, it shows like quite like slightly bigger. It just says like the maximum power is higher than the nominal power. And in our industry, every time we're working on design, we considering like the inverter like datasheet data number for nominal AC power. So there is some discrepancy, and I was wondering if you can expand on that.
Do you want to take that, Janine, or should I?
You can go ahead, Paul.
Yeah, so I think the sizing algorithm, so the stuff that's happening on the input side of SAM is based on the nominal rating, so whatever the nameplate value is.
Mm-hmm.
During simulation, however, we're using the actual parameters, so the hourly values that the model generates as results may show a peak power greater than the nameplate value, except that SAM clips the power to the nameplate capacity. So the nameplate capacity effectively becomes the maximum power.
But let's say on the system design page, you have this modules and inverters, and so the total capacity is the nameplate capacity. Is that true?
That's correct, yeah.
Okay. Yeah, that still doesn't answer my question. Maybe it's just some discrepancy in the model, inverter model itself and CEC database. Just like if you like select some of the inverters, it shows like power capacity is above than the nameplate, and then there's just I'm confused in how what exactly I should use for my overall system size. So
right, it's all about, it's basically a labeling issue, but it has consequences because you're doing any costs, capacity-based costs are going to be based on that nameplate capacity, and also this clipping issue.
Exactly.
One thing to consider is that there's the Janine, maybe if you could show the inverter input page. There's the option to use the CEC inverter model with user entered specifications. So you could, experiment with the nameplate capacity, putting one in that's different from the one that's in the database.
Yep. Yeah, and even here you see like maximum. So the fields that you have right now on the page, it shows maximum AC output power. So in inverters data sheets there are two values. One is nameplate and one is like maximum AC output. So in maximum AC, let's say for 500 kilowatt inverter, it will be like 510 or 520. So which one I should use? That's why nameplate or like actual, maximum AC output power.
Right. So that value is used for two things. One is to calculate capacity-related costs, and the other is to clip the inverter's output in the hourly results. So hopefully that information will help you in deciding which value to use.
All right. Thank you.
Any other questions or comments? Let's see. Here's one. Do you consider introducing options for SI units and currencies other than dollars? We do get that request from time to time because folks are using SAM around the world, and we do not have plans to add unit conversions for currency or other units into SAM. You could theoretically script that, write a script that would allow you to enter costs in other units and then convert them to dollars. And then here's a question about the DC to AC ratio. Maybe I'll unmute your line. Did you want to elaborate on your question?
I'm not very familiar with the DC-AC ratio concept, and I saw that the benefit, like have to be very close to 1. But could you explain a little bit better? I'm not really so familiar with the benefit. For instance, if the DC generated by the panels or the modules would say like it's a 36 volts per module, I would say. And then if I put 10 modules in series, I will have a 360 volts DC. And the AC ratio is the output of the inverter, like 240 volts. And this will give the ratio in the end, dividing one by another.
Okay, so the DC to AC ratio that we see on the system design page, could you show that, Janine? That's a capacity ratio. So we're comparing DC watts to AC watts, and it's the ratio of the array's nameplate capacity to the inverter's nameplate capacity. And it's basically a shorthand way to talk about the relative size of the array and the inverter under reference conditions or under design conditions.
Okay.
And it's just so by nominally oversizing the array, as Janine discussed, it's basically an economic optimization tool, so that you can figure out, it may be worth making your array a little bigger than it might seem would be appropriate intuitively, so that during those few hours of the year when the array operates at its peak capacity, you shed a little power, and then you can get away with buying a smaller inverter or set of inverters. That's the basic idea.
All right, all right. It's about the power, the watts. I was thinking about the voltage, so now I got it clear.
Great.
And I can then play with the power. Okay.
Thanks.
Thank you.
Any other questions? Sorry, there seems to be some issues with the audio this time around. We'll have to investigate that to avoid it in the future. Hopefully, if folks are having a problem with the audio, they can always watch the recording later on. And then there's a question about the SDK. Yes, we do plan to have a webinar on the SDK. Maybe Janine, could you show the webinar schedule on the website? I think it's coming up in February or March. So our webinar schedule is posted here, and that's also where you'll find links to recordings from past webinars is on the learning page of the SAM website. Oh, sorry, I guess I was confusing that we have a webinar on scripting in LK, but if you show the list of recordings of past webinars, we have an SDK webinar that we gave last year. Right. So we're offering a webinar on the new LK scripting language early next year, and we have an SDK, a recording of the SDK webinar that you can go and watch now. We don't have any immediate plans to add standalone modeling to SAM. SAM is a grid-connected model, or a model for grid-connected systems. We do have plans to add a electric storage battery component to SAM. That will be happening probably by the summer of 2015. But no plans for standalone systems. As I mentioned, there are some other models that you can use for that, like RedScreen from Canada and Homer, which is developed by a private company here in the U.S. And then let's see, if there's time, can you touch on some of the issues that would need to be addressed by utility scale projects? I'll unmute you. Could you elaborate, please?
Oh. Can you hear me?
Yeah, go ahead.
Oh, I was just wondering, you focused on the residential grid connected, and I'm sure there's a lot of issues that wouldn't be relevant to the relevant utility scale issues, so for utility scale projects. So it's interesting if there's some of the things that SAM can do that old SAM couldn't.
Okay, sorry, the audio was kind of fading in and out.
What?
There, yeah, I mean that. I think Janine spent a little time talking about the distributed models, so for the residential and commercial financial models on the utility side of things. So for large-scale power generation projects, SAM has a set of financial models for independent power producer projects that that negotiate a power price through a power purchase agreement. And the photovoltaic sizing issues are basically the same. I think the financial metrics that you look at to evaluate the project are different, because you look at things like the internal rate of return and the PPA price, and so on. Maybe Janine, do you have any thoughts on?
Yeah, I'll jump in as far as the second question that you just typed in the chat box. What can new SAM do that old SAM couldn't do in this area? In the PV models, there isn't necessarily so much new functionality, and I apologize if anyone can hear the crashing on the line. We appear to be next to some type of construction in our room at NREL. But we did significantly reorganize the PV inputs, which is part of the big improvement in this latest version of SAM. And then one of the other big additions is that inverter sizing macro that I showed a slide on earlier that makes that HTML window that wasn't necessarily easily accessible in previous versions of SAM and not all in the same place. So that is probably one of the more relevant additions, especially for utility scale projects, where a lot of those issues will still come into play with the degradation and the clipping losses and then the voltages. And I'll reiterate that you can, for your own specific requirements, you can add functionality to that macro on your computer or share that macro with others in your company or network to give additional information that you might be interested in specifically about the inverter sizing.
Okay, if there are other questions, feel free to raise your hand or type the question. Okay, another one from Ihor. Go ahead.
Yeah, I'll ask another one. I read some papers before that some comparison between different modeling tools, and if I'm not mistaken, there was some weak side of the SAM is the model working with thin film models. Maybe I'm mistaken, but I just want to double check. Is there anything I should be aware of working with thin film models in SAM, or it's basically like some work had been done and it's pretty reliable at this moment of time?
Sorry, which kind of models in SAM?
Thin film.
Oh, the thin film.
I can go ahead and take this one, Paul.
Go ahead.
We actually performed our own validation of SAM and several other photovoltaic models last year, I believe, and we published a validation report paper about that. And in that selection of systems, we had 9 systems that we were validating against measured data, and a few of them were thin film systems, and we did not see significantly worse results for thin film systems than for crystalline systems in that validation paper. What you may be thinking of is there is some dispute as to how well the Sandia module model represents thin film modules, and that is one of the options that's available within SAM. However, it is not the only module model, and there is not a similar debate with the CEC module model, which is our default model currently.
Mm-hmm. So you would suggest to use CEC module?
For the thin film modules, yes, I would.
Thank you.
I would also add the Sandia database is you're likely not to find the module that you're planning to use in the Sandia database because it is not being updated at nearly the rate and pace as the CEC database.
I spoke to different module manufacturers regarding using, providing some guidelines from them to use SAM, and their major concern was as, lack of most updated products that they have in SAM. So I think that could be just manually enter the parameters from the datasheet and work. Like, do you think that's the okay approach to use data from the datasheets?
Yes, that should be a just fine approach, and we have that option for both the modules and for the inverters.
Yeah, I noticed that you have you had some bug in your system when you tried to import modules. I believe you are working on the fixing that bug, right?
Yeah, I think there was a note on the thing about known issues a while back for the CEC data import. Those have been addressed and I think are fixed. I think the other thing that when you talk to manufacturers can be confusing is that in older versions of the model we defaulted to the Sandia model, and if you didn't look closely you may not have noticed that we have multiple module databases in SAM. We have both the Sandia module database, the CEC module database, and then you can add your own things, as you're saying, via the data sheet. So the Sandia module database has how many modules are in now? Like 600?
With Sandia?
Yeah.
It's only like 150 or something. It's not that many.
The modules? No, it's more than that. But it's a small number, it's less than 1,000, whereas the CEC module database has like 11,000 modules listed in it. So, I think the other thing that can sometimes happen is the CEC is putting out module updates faster than we can module database updates, and they may not have updated SAM as recently, and so then there's a disconnect between the rate at which modules are being added, or seemingly added.
Mm-hmm. Thank you.
All right, there's a couple of other questions here. There's one about running a parametric study on DC to AC ratio. I just checked, and that variable is available as a parametric input variable, so it should be possible to do that. That's a reasonable question. Sometimes variables are, if they don't get labeled properly, they may not be available for parametric analysis. You may not see them in the list of available inputs. So it's helpful for us to know if you come across a variable that isn't in the list. But I did just check, and it looks like DC to AC ratio is there. And then the question on old and new LCOE, that's a little off topic, but a really important question, and one that we could probably have a whole webinar on, and perhaps should. So I'll just quickly mention that in the new version of SAM, the PPA financial models, so the models for independent power producer projects, now report two separate metrics, a levelized cost of energy and a levelized PPA price is what we're calling them. And the levelized PPA price is equivalent to the old LCOE that we've been reporting in old versions of SAM. And we added this new LCOE metric as something to compare to the levelized PPA price. So the levelized PPA price is a measure of the value of the energy that the system produces in dollars per kilowatt hour, and it includes the basically the project's profit margin that's defined by the internal rate of return. And then the LCOE is intended to represent only the cost of the project without the effect of the internal rate of return. But because the LCOE is, we've calculated it based on an after-tax cash flow that includes debt. There's some some behavior of the LCOE as you vary the internal rate of return that's unintuitive. And that's caused by the fact that the tax cost that we've included in the LCOE cash flow depends on the revenue, which is affected by the internal rate of return. And then also, SAM is the debt model. It's a constant DSCR model with automatic debt sizing, so the debt is sized based on available cash for debt service. So that means that as you increase the internal rate of return, you increase the revenue, which increases the size of debt, and that also increases the debt interest deduction from taxes. So there's a lot of complicated stuff going on in the LCOE calculation that makes it behave in unexpected ways. So that's my very short answer to a good question. We can address this further in the support forum, and we'll be publishing some materials on this fairly soon because we need to make sure that folks understand what SAM is doing. All right, well, if there aren't any other questions, I think we can sign off. Thanks, Janine. Thanks to everyone for participating today. I'll be posting a recording of the webinar on the SAM website on the learning page along with the others probably tomorrow or early next week.